Welcome to Spring LIB.
So we have some constants about this nebula. We have the power, so 5 times 10 to the 31st watts. This is energy lost. We also have the period of 0.0331 seconds. And then we have the change in period with respect to time, dt over dt, 4.22 times 10 to the negative 13th seconds. So the period is increasing every second by 4.22 times 10 to the negative 13 seconds. We also have the mass of the neutron star being 1.4 times the mass of the sun. We have the moments of inertia of a sphere. So this is going to be 2mr squared over 5. And we're going to say that omega, the angular velocity, is going to be equal to 2 pi over t, the period. We know that energy lost by the neutron star is going to be equal to energy released by the nebula. And we can say that the energy of the nebula equals half I omega squared. And we're going to plug in 2 pi over t for omega. So this will be 2 pi squared I over t, given that we have substituted 2 pi over t for omega here. At this point, we can derive both sides and say that dk of nebula divided by dt is going to equal d over dt of 2 pi squared I over t. We're going to have to multiply this here by t over t. And when we do that, we're actually going to be able to see, this would be t squared. We're actually going to be able to relate it to the power lost by the nebula and find our moment of inertia of the neutron star. So if we have this, let's rewrite this. We have dk nebula over dt. This is going to get, again, equal d over dt of 2 pi squared I over t squared. And then we're multiplying this by t over t. We're allowed to do this because it's simply 1. So t over t equals 1. And then we can say that this is going to be equal to 2 pi squared I over t cubed times dt over dt, the change in period with respect to time. We now know that I is going to be dk over dt t cubed over 2 pi squared, and then times dt over dt to the negative first. And this is going to be equal. We can now find our moment of inertia of the neutron star. This is our A. This is our part A. And we have 5 times 10 to the 31st. And we have 0.0331 cubed divided by 2 pi squared. And then this is going to be multiplied by 4.22 times 10 to the negative 13th to the negative first. And at this point, we know that the moment of inertia of the neutron star is going to be 2.177 times 10 to the 38th kilogram meters squared. Let's find the radius of the neutron star. So the mass of the neutron star is equaling 1.4 times the mass of the sun, and the mass of the sun is 1.99 times 10 to the 30th kilograms. These are all tabulated values. And this is going to be 2.786 times 10 to the 30th kilograms. Now, from this, we can say that I, for a sphere, is going to be equal to 2 times the mass of the neutron star, r squared, over 5, which simply means that r is going to be equal to 5 times the moment of inertia divided by 2 times the mass of the neutron star, all to the 1/2 power. We can then substitute, so the radius of the neutron star, this will be our answer for part B, and this is going to be 5 times I, which we found previously, so we're using this value here, 2.177 times 10 to 2.177 times 10 to the 38th, all divided by 2 times the mass of the neutron star, 2.786 times 10 to the 30th, all to the 1/2 power, and this is going to be 13,976.83 meters. At this point, we can find c, the speed of the nebula. So v is going to be r omega, and we can rewrite this and say r 2 pi over t, and we can solve and say this is going to be equal to 2 pi r 13,976.83 divided by t of 0.0331 seconds, and this is going to be, our v is going to be 2.653 times 10 to the 6th meters per second. At this point, we can see how this relates to the speed of light. So v over c is going to be n, and this is going to be 2.653 times 10 to the 6th divided by 10 to 3 times 10 to the 8th, being the speed of light. And this is going to be 0.00884, which means that v, the translational velocity of the nebula, is going to be 0.00884 times c, the speed of light. So this will be your answer, and this will be your answer for C. For D, they're asking us for the density of the neutron star with respect when compared to the density of a rock, of a normal rock on Earth. So D would be density equals the mass of the neutron star divided by the volume of the neutron star. And this is going to be 3 times the mass of the neutron star divided by 4 pi r cubed. Again, the volume of a sphere is going to be 4 over 3 pi r cubed. And at this point, we can find the density. So density is going to be 3 times, again, 2.786 times 10 to the 30th divided by 4 pi 976.83 cubed. And this is going to equal 2.436 times 10 to the 17th kilograms per meter cubed. The density of a rock on Earth is approximately 3,000 kilograms per meter cubed. So N would be rho divided by rho of the rock, rather. Sorry, this is not P, this is rho. Rho denotes density. And this would be 2.436 times 10 to the 17th divided by 3,000. And this is going to be 8.12 times 10 to the 13th. So that means that the density of the neutron star is 8.12 times 10 to the 13th times the density of a rock. So it's 13 orders of magnitude higher than the density of a rock, which is extremely high. And then we're trying to find the density of the nucleus with respect to the density of the neutron star with respect to the density of the nucleus. So here, density of nucleus would be 10 to the 17th kilograms per meter cubed. N will be P of the neutron star divided by P of the nucleus. And this would be 2.436 times 10 to the 17th divided by 10 to the 17th, 2.436. They're on the same order of magnitude, so they're about equal, which makes sense. The density of the nucleus is going to be about equal to the density of the neutron star. And so this would be our answer for D. And that's the end of the solution. Thank you for watching.